Given this new rational function and that we are trying to identify the domain using interval notation, we will need to factor both the numerator and denominator. And those factors are 3 times the quantity 4x plus 1 all over the quantities 2x plus 7 and 4x plus 1. Since we cannot allow our denominator to equal 0, we will need to realize that 2x plus 7 can't equal 0, and therefore x cannot equal negative 7 halves. Just as 4x plus 1 cannot equal 0, and therefore x cannot equal negative 1/4. So as we remove those from all reals, our domain becomes negative infinity to negative 7 halves, negative 7 halves to negative 1/4, and negative 1/4 to infinity. We move on to removable discontinuities. We must remember that we're looking to remove factors from the denominator. We have a quantity that happens to be 4x plus 1 found in both the numerator and denominator. So it is that 4x plus 1 that can be canceled that we know when it equals 0 occurs when x equals negative 1/4. This is why we will have a removable discontinuity at x equals negative 1/4. Identifying infinite discontinuities require us to find factors that did not cancel out. In this case, 2x plus 7 did not cancel, and therefore x equals negative 7 halves is where we will find an infinite discontinuity. Infinite discontinuities also tell us where vertical asymptotes are. And because we did find an infinite discontinuity at x equals negative 7 halves, the equation x equals negative 7 halves is a vertical asymptote. Identifying the x-intercepts requires us to determine which values of x will make the numerator equal to 0 while making the denominator a non-zero value. So we will cancel out any equivalent factors found in both the numerator and the denominator. In this case, it's the quantity 4x plus 1. We find that only 3 remains in the numerator. But since 3 never equals 0, our numerator will never equal 0. Thus, there are no x-intercepts. We need to look at the polynomial's left and right end behaviors when identifying the horizontal asymptotes. A rational expression has a linear numerator. It's being divided by a quadratic denominator. When the lower degree of one polynomial is divided by the higher degree of two polynomial, the limits as x approaches both negative and positive infinity will converge to a specific value, or height when you think of its graph, which for this example is 0. Therefore, the equation y equals 0 is a horizontal asymptote. After our original rational expression is simplified into 3 all over the quantity 2x plus 7, we can look at this newer simplified expression's graph and verify that its domain does not include negative 7 halves, as there is infinite discontinuity and thus a vertical asymptote at x equals negative 3.5. Despite sharing a horizontal asymptote of y equals 0, this particular graph does not represent our original rational expression, as it fails to show the correct domain. This updated graph correctly represents the quantity 12x plus 3, which is divided by the quantity 8x squared plus 30x plus 7, because it shows both asymptotes as well as the removable discontinuity that is occurring at x equals negative 1/4. In our final rational function example, we have a cubic trinomial being divided by a cubic binomial. We need to factor each of those cubic polynomials in order to identify the domain. Although I will not visually show you all the steps, I will say that I first factored out an x from both the numerator and the denominator. Then I took each of the remaining quadratics and used my factoring skills to break them down into their linear factors. Having 3 distinct factors in the denominator means that we may have 3 distinct values of x that could lead to a 0 in the denominator. Going through the work, our domain will be all reals except for the values of negative 3 halves, 0, and 3 halves. The removable discontinuities occur because both the factors x and 2x plus 3 will cancel out when simplifying, and when each factor is set to 0, we find that removable discontinuity occurs in 2 locations, when x equals 0 and when x equals negative 3 halves. There will be an infinite discontinuity because the denominator still has a factor of 2x minus 3 which did not cancel. And when set to 0, we find out that x equals 3 halves is where infinite discontinuity occurs. And because we have infinite discontinuity at x equals 3 halves, we also have a vertical asymptote of the equation x equals 3 halves. X-intercepts occur when your numerator equals 0 while your denominator does not. And with 5x minus 8 in the numerator not canceling, we set that equal to 0, and we say that an x-intercept will occur when x equals 8/5. Horizontal asymptotes are all about end behaviors. End behaviors means we need to understand who the playas are. And with a third degree numerator and a third degree denominator, we can take each of those coefficients, 10 and 4, and we divide them out. And we realize that this end behavior will converge to 10/4, which we could call 5/2. And we can then say that there is a horizontal asymptote when y equals 5/2. One last time to remind you, write the equation y equals 5/2. And we've reached our last slide. And we'll recognize that a rational expression of a cubic divided by a cubic has had two sets of factors cancel out in both the numerator and denominator. They are x and 2x plus 3, leaving us a simplified expression of 5x minus 8 all over 2x minus 3. And for one last comparison, we'll look at that simplified expression's graph. We acknowledge that yes, it does share the same vertical asymptote as x equals 3/2, as well as the horizontal asymptote as y equals 5/2 of our original cubic over cubic. But this graph does not properly show the domain because it does not show removable discontinuities. This graph does. This graph shows that we have a removable discontinuity at -3/2 and 0, and therefore need to be pulled from our domain, just like we pull our infinite discontinuity of 3/2 from our domain as well.